So the good news is that the last coursework has been moved to the new year. In fact, on the 18th, because you have already the deadline on the 11th. We have another one of January, so the 18th of January. So it's a long time ahead. I never had such a deadline in the past, but maybe this year there is something happening. So.
What kind of deadline do we have on the 11th?
On the 11th, there is a deadline by Mark Hubster, I was told, January. So, but must be some other course. So,
okay.
Then I thought to have it on the 18th, so that you don't have two deadlines at the same time. Thank you. So,
It's research methods. Come on, they have to toughen it out.
No, for this last year, which I think he's putting in.
Right. Before Christmas, then let's say that I'll give it to you next week. So you have a lot of time.
It would be a good idea for us to have at least a little bit of time when we have to ask questions if there are some.
In the new year. So, not during Christmas.
Answer emails on the 24th.
Well, no, let's say after the 6th, 7th. But there is also a mail submission in the mail and ask questions. Let's say 10 days before.
Which mailing list?
We should be.
We only got submitted the last 20 minutes.
Second.
Because we hadn't realised about the new what is missing. Yeah. So we sent a message to Mark saying, "Wait." It was, yeah, but yeah. But it wasn't. We only realised that.
Do you have any slides left?
No.
Before I put the back.
They are in the Moodle. Maybe I can bring some. Any other questions about last lectures or anything? So the last two lectures are a bit more advanced. And they might be in the exam, so pay some attention. However, I will present some proofs, and this will not be in the exam. So just like that. But if you want to understand this stuff, and perhaps use some of these in the research project or whatever, I think it's important to make an effort and go through the proofs. A little bit of this might be in the homework. So. But I would say, generally speaking, it's a bit more advanced than the other part. So today we discuss sparsity methods. Anyway, have you heard about the lasso or lasso method? Has anybody heard of it? So we will discuss in some detail this method and some extensions of it. So the idea is that, unlike ridge regression, so we discuss linear models. So we just want to estimate the parameter of the linear regression or linear classifier, like perceptron I heard before. But we will consider some regularization methods which make different assumptions on the configuration of the parameters of the model, so the underlying function which generates the data. And we will assume in particular sparsity, so some of the parameters will be equal to 0, right? So this is the idea of the lasso. And then we'll extend these in different directions. And in particular, we'll go to problems which involve matrix completion or multitask learning. Then if there is time, we'll discuss also some nonlinear modeling, so some nonlinear extensions of these methods. Then another topic which I want to cover, I'm not sure how much time we have today, so the second notes is how do you solve. So today we'll formulate some regularization problems. but I also want to discuss a little bit how do you solve the problem, right? So, in the case of ridge regression, you have to solve the linear system of equations, so it's very easy. In particular, MATLAB does it for you. Here it's a bit more complicated, so it's important to gain some understanding about.
Sorry. There's some hair flying here.
So there is some air. Let's see what's going on.
No, it's a student.
Very interesting. I'm afraid you need to move over there.
Well, never mind. I would move later.
No, but when you close the door, it starts the ventilation, so it's fine.
Oh, I see. Then we can shut it off.
You can leave it half closed or something.
First, let's research if it's really.
I already had trouble with this, so I think this cannot be fixed. So what I was saying, and that's the plan for today and the next week. Maybe after next week. Then I will speak a little bit about multitask learning if there is time. There was also an idea which I mentioned in the past about application to neuroimaging, but that has been cancelled because my colleague is in a conference and she cannot make it. But you will still hear a little bit about this topic during the project day next year. So she, Janaina, Miranda, she will give some project related to that. Right. So we begin with L1 regularization or the last one. So the idea, so the original formulation the original formulation is to do, so you minimize the square error, right? So like a ridge regression. So instead of having a regularization here, you add the constraint. This was just the original formulation, right? But you know that this problem is equivalent to this. So normally when people say lasso, they refer to this problem, even though the original problem considered this one. So the question here is that how do we solve this problem? So this is the L1 norm. It's the sum of the absolute values of the components of the weight vector. Right? So it's very different from ridge regression because in ridge regression we have this penalty, the L2 norm squared. So what happens here is that, as we will see, this L1 norm favors many zeros in the solution. So it can be seen as an approximation of the function, the regularizer, which counts the number of non-zero components. So here you try to bias solutions which are sparse. So that's the say the hand waving or intuitive rationale behind this such method. So this problem is equivalent to this other problem, which is a quadratic programming problem, right? So you can see that so if you write each component of W as a positive component minus a negative component, right? You can always do that, right? Then you see that if Wj happens to be positive, the second one will be 0, and conversely, if it is negative, Wj plus will be 0. Right? So therefore, the L1 norm can be written as this term, Okay, so the L1 norm is the sum of the L1 norm of the plus the L1 norm of the minus, right? We understand that only one of the two will be different from 0. Yes?
Sure, I don't understand the W plus and W minus what. You might give an example, sure.
Yeah, these are you can always take a number and write it as a difference of two positive numbers. And the most parsimonious way to do that, if the number is positive, you just write as the positive. If it is negative, as negative. So you can always do this, right? And then you can consider this problem, right? Where the first term is exactly as before. You have just used the representation of the W, right? So because of this equation, W is W plus minus W minus. Where W plus is the vector formed by the W plus J, and W minus by the W minus J. Right? So the first term here is the same as the first term here. The second term is different. However, since you minimize over W plus and W minus, the smallest, since you minimize, it will always be the case that at the optimum, either Wj plus will be different from 0 or Wj minus. Right? Otherwise, you obtain a larger objective. Right? So, the first term depends on the difference. Right? The second term, the sum. Right? So if you think about it, since you minimize, only one of the two will be different from 0. So only one of these two. So this is a slick proof to say that the original problem is the same as minimizing a quadratic programming problem, minimizing a quadratic objective with linear constraints. Actually, very simple linear constraints. There are non-negativity constraints. So the two problems are the same.
And the E transpose?
Well, E is just a vector as all components equal to 1. Yeah, so this thing here, as I said, is the sum of the J of Wj plus Wj minus. Right? And because of the constraint, is the sum of positive numbers, right? So you gain if you just choose one of the two to be different from 0, right? Because the error term depends on the difference. But does it make sense? Yeah, so what I'm saying is that, let's do it in one dimension. So what I'm saying that if you have, for example, you have W, let's say that now these are just numbers, as you have this, plus this. Actually, this is a bit too stupid, because the minimum will be 0. Yeah, let's say 1 minus. So you have this objective function, right? And you minimize over, right? So this is 1 minus W plus W minus, right? So it's clear that the minimum will only, what will be the minimum in that case? It would be, actually I don't know, but it's clear that you only want one of these two to be different from 0, right? And in this case, you will want W plus to be different from 0, right? Because then you go closer to 1, and you make the error smaller, right? So here the solution will be W minus equal to 0. And then, right, so you have to minimize over W plus 1 minus W plus. Where we forgot the one of the two. That's important. Plus. So then you have to solve this problem. We'll see in the next few slides how find a solution of such problem. So the message on this slide is that the original problem, which involves the L1 norm, okay, so the original problem, it is not so pleasant because this is a sum of absolute values, so it's non-differentiable function, as we will see in more detail. Right? However, it's equivalent to a constraint optimization problem, in which the objective function is quadratic, convex, and the constraints are just linear constraints, positivity constraints. So, okay. So in fact, the previous problem, if you use MATLAB, there are two boxes for solving problems of that type. So, however, it might be time-consuming to use these two boxes if the problem is large scale. So if you have a lot of variables, so if the vector W has many components. So what we will discuss today and next week are efficient methods which are tailored to such problems, so they're faster. Now let's consider a special case of the lasso, which is similar to the previous one I was describing. So in general, the objective is x times w, right? So where x is the input matrix, right? Y is the output vector. But let's consider a case in which the data matrix is the identity matrix. It's a very special case. So in general, we will have x, which is let's see, I think we use the notation m or n, m times d, right? So the rows of the matrix x are the data points, d-dimensional, right? And they are m in number. Maybe elsewhere where we use n, doesn't matter. But here we choose the case in which m is equal to d and x is the identity matrix. So in this case, you can solve the problem in closed form. There is a formula, and which you can derive by doing some case studies. Right? And the formula is given by this function. Right? So you introduce this function, h lambda of t, which is called the soft threshold operator. Well, so you take a number t is a real number, and you take the absolute value, you subtract lambda to it, and then you take the positive part. So if the absolute value of t is more than lambda, the result is 0, otherwise it is the absolute value minus lambda. So this function t minus lambda plus, right, is something like that. Right. It's 0 here, and otherwise it's linear. Okay. So the solution of the lasso problem for when x is the identity matrix is obtained by applying this function, this operator, to each component of the output vector y. Okay. So in this special case, the output y has the same dimension as w, because x is the identity matrix. And then the solution is given by this formula. Now the reason for that is the proof is explained here. But so first you observe that the problem involves many variables, but because of the choice x equal to identity, it decouples across the variables, right? Because the first term is the sum, is 1/2, and then the sum over I, and then you have wi minus 1i squared, right? This is the first term, this one. And the second term is lambda times the sum over I, absolute value of wi, wi. So you can all write like that, right? Sorry. put the 1/2 here. So it's a sum over I of objective functions only of the component wi. Let me do it again because that's okay. So the first term is 1/2 sum over I yi minus wi, whatever. Second term is lambda times sum over I absolute value of yi. Right? Now this thing is the same as the sum over I and then this function. Right? Okay, so since we want to minimize over wi, and here we don't use the constraint, but we use the formulation with the absolute value, then the minimum is obtained by minimizing each of the functions under the sum independently. Okay. And then you need to understand that the vector wi at, right, which minimizes this objective, is given by this formula. And then so here you proceed by consider different cases. So first you observe immediately that the minimum, the minimizer, must have the same sign as yi, otherwise we increase the objective, right? So it must be the case that the sign of wi hat, right, is the same as the sign of yi. Right? So actually, let's change the notation to simplify. So let's consider this problem, right? So we minimize over t. Enough. Sorry. Minimize over c. C minus d squared. So each of these problems is of this type. And then if you consider the various possibilities, you see that the solution is given by this formula. So C hat is equal to H lambda of T. Okay. So the solution is 0 if the output is small in absolute value. Otherwise, right, so the solution is given by this function. Right? Well, almost. So this is what the result says. Right? So the solution is equal to 0 if, so going back here, so one component of the solution vector is equal to 0 if the output yi is smaller than lambda. Otherwise, it has the same sign as yi and is stay close to it linearly. Right? So the solution is given by this formula. Right? So it's 0 up to here, and here it becomes positive. 0 up to here, and then it becomes 0. So this is the plot of the function h. Okay. The solution also is unique because the function that we minimize is strictly convex. So we know that from analysis that if the function is strictly convex and it grows at infinity, like this one, there is a unique mean. Okay? We say so here the argument is quite. Then you consider two cases. So in the first case, if the solution is different from 0, you can set the derivative equal to 0 because the function is differentiable. Right? Then you set it equal to 0, you try to solve it. If you cannot solve it, it must be the case that the solution is 0. So that's the way it works. But I think this is an important thing to understand. But it is used over and over. You want me to explain it again? It's fine. Yeah. So, there is another way which is more sophisticated to approach this problem. Right? And it uses the directional derivative. Right? So now we need to open a short parenthesis about how to identify the minimizers of, say, complex optimization problems. So the important tool is provided by the directional derivative and the subgradient, as we will see in the next slide. So the directional derivative is similar to the derivative, but it is taken only along one direction as opposed to both directions. Right? So you take the limit of the difference of the function, w plus epsilon times the direction, and epsilon is approaching 0 on the positive side. Okay? And then you have the following results, right? Which says that if you have a complex function f, which should have been written there, then w hat is the solution of the minimization problem if and only if the directional derivative of the function f at w hat, right, at any direction is more or equal than 0. Right? And this has a intuitive geometric meaning. Right? So it means that if you try to approach this vector for every direction, right, it is more or equal than 0, which means that the function at w hat is always going to be smaller than along any ray, right, which approaches w hat. Right? So, if the function is differentiable, which doesn't need to be the case for complex functions, then there is this result. You say the directional derivative is the same as the inner product between the direction and the gradient, right? And therefore, the theorem says that w hat is a minimizer if and only if the gradient is equal to 0, which is a well-known result for optimality, right? So this is an extension of optimality condition for differentiable function to differentiable complex function to general complex functions, like the one that we just saw. Right? So the previous problem is the function is that we discussed more, but this function is convex, but is not differentiable at 0, right? Because I'll make a picture in a moment. So sure, let's make it here. So because this function is quadratic, but this function is something like that, in one dimension. It's the L1 norm, so it's an absolute value. That's it. So here is not differentiable. So a couple of slides. So before going back to the problem, a couple of slides on so optimality conditions. Another notion we can define, which is related to the directional derivative, is the notion of subdifferential. But these are not very important for the course, but they're just here because we use them heavily when we discuss optimization algorithms. Okay, they're a bit advanced and it's difficult to convey fully the idea of why these notions are needed. But, so they play an important role in the analysis of these optimization problems and in the study of iterative algorithms to solve the problems. So the notion of subdifferential is the subdifferential of a convex function f at w is a set, right? Is a set of vectors, which when the function is differentiable is just the gradient. So it's a natural extension of the notion of gradient. Right? So the elements of, so the subdifferential is a set, and the elements of this set are called subgradients. When the function is differentiable, the only element is the gradient. So it's a natural extension. Right? So it is defined by this equation. It's a set of all vectors such that the value of the function f at every vector v is greater or equal than the linear approximation, this linear approximation of the function at w. Right? So w is fixed because you consider the subdifferential as w. Right? U is your vector in the set which needs to satisfy the following constraint. So for every vector v, the value of the function is v is greater or equal than the value of the function at the fixed vector w times this linear term, which is u linear product with v minus w. Right? So if you consider, let's make consider this function, right? And if we stay here, right? So this is, let's see if I can manage to do it. So this would be my w, right? And then I'm going to look at this function, f of w plus u transpose. But in this case, right, if I take in this case, u is going to be a number because I'm in one dimension. So I can choose it to be equal to 1, 2, 3, minus 1. If I choose it appropriately, now this function here is going to be tangent here, right? It's going to be a line. And so in this case, there is only one vector u, which in this case is a number, such that the linear function stays below the functions everywhere, right? Because this vector v is everywhere. So this equation says that the linear approximation is below, is a underestimator of the function. In this case, there is only one direction, only one vector. Sorry, there's only one vector u. Right? It doesn't need to be a direction; it could be different size, which stays below. But in this case, it's just the derivative, the gradient, more than one dimension. If I consider this function, right, happens to be the L1 norm that we used before. And if I take this point, right, now here there are many lines which are an underestimator of the function, right? Because I can consider this one is below, this one is below, this one is below. Right? And here, if you think about it, you see that every vector u, such that the absolute value is less or equal to 1, makes this inequality work globally. So in this case, the subgradient of the L1 norm at 0 in one dimension is a set of all vectors which have absolute value less or equal to 1. So it's an infinite set. So there is this geometric meaning, and then, so why do I tell you about this stuff? Is because of this result. So the result says that w hat is a minimizer if and only if 0. So the 0 vector belongs to the subdifferential of f at w hat, right? Which again, if f is differentiable, this means that the gradient of f at w hat is equal to 0. So again, it's a natural extension of the optimality condition for differentiable functions, convex functions, right? So, right.
I'm sorry.
Yes.
While we were at it, could you also make a sketch for the directional derivative for the L1?
Yeah, we'll do it. We'll do it in 2 slides. Yes.
Okay.
Yeah, it's important. 3 slides. You want. So Yeah, so this is just repetition, I think, for the And then, as you become comfortable using these things, which are not, as I said, don't be scared, they are not central for the course. Okay, so, there is a significant group of people in machine learning use these things frequently and to derive new algorithms, to study the properties of algorithms. So if you're interested, here there is some preliminary information, but if you're not, I'll say today and this week, more advanced lectures, so don't be scared. Okay. If you're interested, ask me questions. So there is some algebra of these subgradients, so which are again natural extension of gradients. So you can take the subgradient of a scalar times a function f is obtained by taking the scalar times some error here. Yes. So just multiply the set times a. So the subgradient of a function which is obtained by multiplying f by a scalar is like the subgradient of f times a scalar. So if it is a ball, it becomes bigger or smaller depending on the age. The subgradient of the sum is the sum of the subgradients, again the sum of sets, and there are other properties which one can add. Right. So, right, oh, here we are. So we go back to our problem and we see that this stuff is useful in proving the optimality condition. There are the formula for the minimizer. So one way we've done it before in a more ad hoc way, right, which is very fine, but it worked because of the simplicity of the problem. The way we do it now, it also works for other problems, in which instead of the L1 norm, you have some other complex functions. Okay. Whereas the other approach, which we did before, so as I said, it's very much specific to the Lasso problem. So either you play tricks or you use general principles, which say, either you walk along the main path or you look for shortcuts which work only specifically some problems. So here, so you need to know what the sub-differential is of the L1 norm, right? So what you asked. And so yeah, it's interesting because we use some of these properties that I mentioned. So first of all, so this is the optimality condition, right? Because so the W hat, so here is called W. W is a minimizer if and only if 0 is in the subgradient of this function, right? The subgradient of this function is equal to the sum, the set sum, and the subgradient of the first term plus the subgradient of the second term. Here we forgot one. There are some typos in this. Now, the subgradient of the first term is just the gradient because it's differentiable, and we do computation, and we get the subgradient of the first term is the set which contains only the gradient, which is equal to x transpose x y x w minus 1. So the derivative of the quadratic function, and you get that one. Right, so 0 must be in this, plus the subgradient plus lambda, because we use the other property, the subgradient of the product of the function times the scalar, to take the scalar out. Right, so the subgradient of this is lambda times the subgradient of the L1 norm. So all we need to know is the subgradient of the L1 norm. Okay. So I repeat. W is a solution of the problem. If and only if 0 is in the subgradient of this function, and then I use my two rules, right? That the subgradient of the sum of function is the sum of the subgradients. So that's why I have this sum. And the second function is lambda times L1 norm. The subgradient of that is lambda times the subgradient of L1 norm. So, right? And then this I have rewritten here in this form, right? Because as you see, here there is a minus y, here is y minus, so I just changed the sign, right? So 0 is in this set if and only if this vector minus is in this set. Okay? So I use some set theoretic equivalence. So we need to compute the subgradient of the L1 norm. So if you're not used to these kind of things, they are not easy, I think. So you need to kind of enter into the right mind frame. To compute the subgradient of the L1 norm, we go back to the definition and we try to reason about, right? We try to reason in this case. So what we need to, right? So, all right. Also, before doing that, so this is the L1 norm is the sum of the absolute values of the component of W, and we know that the subgradient of the sum of functions is the subgradients of each of the functions. So all we need to know is the subgradient of the absolute value of a scalar variable, right? Because then we will sum this up over all components. So this is what we need to know. And then we wrap it back and we. So this is what we need to know. For now, this is what we have done before, right? But let's do it again. So the absolute value is this function. We have t, and here I have the absolute value of t, right? Now, if t is different from 0, the function is differentiable, and it is either plus or minus 1, depending if I'm on the right or the left side of the y-axis. Otherwise, as I said, it's the set of all u such that the absolute value of u is less or equal than 1. Right? But it is that's what it is. Right? And therefore, for the subgradient of the L1 norm of W, right, what is it? Is it equal to all vector u, right? Such that ui is equal to the sine of wi if wi is equal to 0, right? Otherwise, it is equal to ui is equal to otherwise ui is less or equal to 1. It's not very well written. So you apply it component wise because that's the sum of sets. So using this tool, we right. So using this tool, for example, here we can confirm that the solution that we found before is also found through these tools, right? And so you see, so we take the case x equal to the identity. Right? So we go back to this equation, and we now analyze it, having discovered the formula for the subgradient. Right? So what this equation says, so it can be applied component one, right? Because x is the identity, so component wise, Well, this equation says that yi minus w hat I, right, will be equal to lambda times the sine of w hat I if w hat I is different from 0. Otherwise, it will be this thing here, right? Right? And then you can verify that then it's a bit complicated, but you can verify that the solution that we stated before on page 4 satisfies this constraint. And since this constraint, this qualification constraint, so since these are necessary and sufficient, it would be a minimizer. Right? So we can go back here. Right? Oh yes. So actually, the formula I seen right here. So the formula was that wi hat was equal to the positive part of yi minus lambda plus times the sine. And yeah.
Sorry, now you're
Yeah.
showing that the special case and the general case deliver the same results, right?
No, almost. So here I derived optimized the condition for the last, so which are these. So this vector must be in the subdifferential times lambda, and by the subdifferential we have computed. So this will apply to any choice between these x. What I was going to do is that if you choose x to be the identity, the vector we derived before by some more intuitive reasoning satisfied this condition.
Why do you choose x to be the identity?
For the sake of understanding, so to make
Just
to make it
special
simple
case.
and verify that in that case this works in every case. But in particular, if you choose x identity, you can verify that you can have confirmation that it works. So, right? And this is pretty much what this condition says, because you have this guy must be less or equal than lambda, right? This vector is less or equal than lambda, right? And or right when this vector is different from 0, which means when the absolute value of yi is bigger than lambda, then you must have the same sign as must satisfy this condition, right? Which is also true, right? So it works. So this way of working out the problem is less intuitive. It's a bit more sophisticated. But this is just to consider a simple case where you see line by line it works. Yeah.
So we get the bounds on our estimator. W is the
Then you find a solution. It's not a bound.
well for the case where it's for the case where it's equal 0,
Yeah.
we have only some bound.
Yeah, but so that this bound is to verify that a certain vector solves the problem. Yeah. But it is not a bound of the solution. So it is not that. So a vector W solves this problem. The solution of this problem, by the way, is in general not unique. Right? When x is identity, is unique because the function is strictly complex. If it is not, so if sorry for the short parenthesis, if the number of rows, if the number of data points is more than if the sample size is more than the number of dimensions, this function is not strictly complex. So the solution, it will be infinite solution of the problem. However, they will all have the same minimum value because the problem is convex. So what I'm saying is that it is something more like that. all these points are a solution. But what this result says is that every solution must satisfy this equation. Right? So if you can solve this equation, but there are some complicated nonlinear equations, so they're not easy to solve. So I'm not pretending that we solve these equations in general. So this will be solved by some numerical optimization method. Right? But you can verify at least that when the matrix X is the identity, these equations are simple, right? And there is a unique solution, as we know, and that is the one that we derived before. So you can verify that in that case, this is the solution, right? The one that we derived here. So the solution is given by the Soft-Schrödinger operator. This vector satisfies this equation. It's the only one that satisfies these equations. So if you go through so if you understand what the set is and you work it out, you see that that vector, right, that we claim be the solution, we verify. Indeed, also following this reasoning, it is confirmed to be the solution. Right? And since this is a set, so you need to verify that some inequalities are true in some case, otherwise there is an inequality. So it's so we stop soon. Yeah. So what we see after the break are some extension of the this problem. So we will see some problems in which we have an error term f of w, and then we have a regularizer g of w, which here we took the one all, and then we consider other ones, and we see how to solve the problem. We can understand the rationale for using these regularizers, and we build on that. So we stop for 10 minutes.
So I wasn't entirely sure about the motivation of this thing, but in fact it's just a theoretical result. Okay, sorry. In fact, he wouldn't really verify anything.
I didn't step on anything.
Not this time.
You cannot use the tool.
There's always been an opportunity if you